Hello learners, welcome to this course on Fundamentals and Programming of 8085 microprocessor. In this tutorial, I will be discussing about on how to interface a keyboard or 7-segment display controller which is 8279 with 8085 microprocessor. So an 8279 IC is used to interface a matrix keyboard or a 7-segment display with 8085 microprocessor. So it can be used for both interfacing a matrix keyboard as well as a 7-segment displays. So we have two modes of operation. Either I can select a keyboard mode or a 7-segment display mode for operation. It can also be used as a strobed input port. So we can use it as a simple input port also with the help of this 8279 IC. So but generally it is used as a keyboard interfacing. So here I show the architecture of this 8279 IC. So here we have the center block, data buffer, IO control, control and timing registers and timing and control block are common for both your keyboard operation as well as display operation. So on the right side you have the blocks related to keyboard operation like FIFO sensor RAM status, 8x8 FIFO sensor RAM, keyboard debounce and control block, return block and a scan counter. So this relates to the keyboard side, and on the display side we have display address register, 16x8 display RAM and display registers. So now let us discuss this architecture in detail. So the data buffer, it gets the data whenever there is a valid key press in a keyboard mode. Whenever there is a valid key press, then the data will be stored in the 8x8 FIFO sensor RAM. So here we can able to store 8 byte data. So 8 key presses can be stored in this RAM. From this RAM, the data can go to this data buffer. From this data buffer, the CPU can read the data. So the status of the FIFO RAM is indicated by this FIFO sensor RAM status. So this FIFO sensor RAM status is a 8-bit register. Here you can see it's a 8-bit register. It indicates the status about the FIFO sensor RAM. So for example, the lower 3 bits represents how many bytes of data are available in the RAM. How many key presses are there in the RAM. That is indicated by this lower 3 bits. Then F stands for whether the FIFO RAM is full or not. If I have a valid key press of 8, then in that case the FIFO sensor RAM will get full. So that is indicated by this F flag, and U flag is used if the data is read by the CPU from the FIFO sensor RAM, it will get empty. So once the FIFO sensor RAM does not have any valid data, that is indicated by this U flag. Then there is a overrun flag. So overrun flag in the sense I have 8 key presses indicated in the FIFO sensor RAM, and when there is a 9th key press before reading the data by the CPU in the FIFO sensor RAM, if I have a 9th key press, then the already available content in the FIFO sensor RAM will get replaced. That will be indicated by the overrun status. So before reading the data from a FIFO sensor RAM, if a new data comes into the FIFO sensor RAM, then it is called as a overrun status. Then I have SRE flag to check whether I have multiple key has been pressed or not. Then display whether it is available or not. So this is a FIFO status register contents. So there is also a keyboard debounce and control circuit. So whenever we have a key press, it will induce oscillations before it settles down to a stable value. So this oscillation should not be considered as a valid key press. So in order to avoid that, the very first key press will be recognized and the other oscillations will be nullified. So that will be done by your keyboard debounce circuit. And then there is a scan counter and a return counter. So the scan counter will be set by the microprocessor. It will try to scan one by one lines and it will try to take the corresponding values in the return lines. So depending upon a valid key press, a particular return line will get activated. So that can be identified, and depending upon that, the FIFO RAM status will be updated. So we have a control and timing registers. So here the configuration of this IC, whether I want to use it in a keyboard mode or in a display mode, so that will be decided by this control registers available, and it will generate the corresponding timing informations required for both your keyboard as well as the display. So now let us go to the display part. So in the display part, I have 16 by 8 display RAM. So here in the keyboard part, we have 8 by 8 FIFO sensor RAM. Here we can store valid key press of 8. So 8 key presses we can able to store here. Whereas in case of a display RAM, I have 16 byte data is available in the display RAM. So we can send 16 characters. It can be saved in the display RAM. And from the 16 characters, a particular character will be selected by the display address register, and it can go to the display register for visualization. It will get connected to the 7-segment displays through these lines. So 16 characters can be stored onto the display RAM, and the location of the character will be identified by the address register, and that data will go to your display register, and the display register will be routed to your 7-segment display. So this is the architecture of your 8279 IC, which supports both keyboard mode as well as a display mode. So now let us look at the pin details of your 8279. So here in 8279, it's a 40 pin IC, dual inline package IC. So here you can see pin number 38 is RL0, pin number 39 is RL1, RL2, RL3, RL4, RL5, RL6, RL7. So these are the return lines. Then we have a scan lines, SL3, SL2, SL1, SL0 is a scan lines for your keyboard. So these are the return lines for your keyboard, these are the scan lines for your keyboard. Then there is also two more key, control key and a shift key in case of a keyboard mode. And in order to generate the timing information for the 8279, it requires a clock signal. So the clock signal is available here. So whenever we have a valid key press, that can be indicated by an interrupt sent to a CPU. Then the CPU can read the RAM and get the data. Same way the IC can be reset. There is a control lines like RD bar and WR bar. We can read the key press, which key has been pressed. Same way we can write the data onto the display. Same way we can write the control word registers. DB0 to DB7 represents the data lines connected to your data bus of CPU. Then there is a pin number 20 is ground line, pin number 40 is a supply line. Then I have out B0 to B3, A0 to A3. So this is for your 7-segment displays. Pin number 23 is blank display. Pin number 22 is for selecting the chip. And pin number 21 is for A0. So this A0 will be given by the CPU. If it is 0, command register will be identified. If it is 1, data register will be selected. So now let us start with the keyboard interfacing using 8279. So the keyboard first scans the keyboard and identifies if any key has been pressed. It first checks whether any key has been pressed. If it is pressed, if a valid data is available in the sensor RAM, then the relative response of the pressed key will be sent to the CPU. So the keyboard can be interfaced in two modes, interrupt mode or in a hold mode. So interrupt mode in the sense, whenever a valid key press is there, it can interrupt a CPU and ask the CPU to read which key has been pressed. That is an interrupt mode. So the processor is requested service only if the key is pressed. Other times, the CPU can continue its main task. In a hold mode, CPU periodically reads an internal flag. It continuously checks the internal flag, whether any key is pressed. So thereby the CPU will not be able to do any other job. So it needs to continuously monitor your keyboard, whether a valid key is pressed or not. So this is called as a hold mode. So it can be operated both in interrupt mode as well as in a hold mode. And in the keyboard mode, we can connect up to 64 keys. Plus 2 special keys can be connected. So in keyboard mode, I have 3 types. One is scanned keyboard mode, scanned sensor matrix mode, and a strobed input mode. So scanned keyboard and the sensor matrix are similar in nature. Here in the keyboard mode, we use switches for a valid key press. Instead of that, if I put a sensor, it is called as a scanned sensor matrix. Instead of a switch, we place a sensor. So again, this sensor will be a digital sensor. It will act something similar to that of switch, on or off. Strobe input mode, which means I can use it as an input port for your microprocessor. So in the scanned keyboard and scanned sensor matrix, again I have 2 modes, encoded mode and decoded mode. So in encoded mode, more number of keys can be interfaced, whereas in decoded mode, less number of keys will be interfaced. So first start with scanned keyboard mode. So this will also be applicable for your sensor mode, scanned sensor mode. So here in the difference between the keyboard mode and the sensor mode is, in keyboard mode we connect switches. In sensor mode we connect the sensors, digital sensors. So first let us start with the decoded mode. So in a decoded mode, a matrix keyboard can have only 4 rows and 8 columns. So here you can see it has 4 rows, SL0, SL1, SL2, SL3. It has 4 rows and 8 columns, RL0 to RL7. So these are the scan lines and these are the return lines. So 8 into 4, we can connect 32 keys here. In the decoded mode, I can connect 32 keys plus 2 special keys, shift key and a control key. So altogether 34 keys can be interfaced in your decoded mode. So at each intersection of a row and a column, okay, so there is an intersection between a row and a column, we connect a switch in terms of a scanned keyboard mode. In terms of a scanned matrix, sensor matrix mode, instead of this switch, we connect a sensor. And this sensor will be a digital sensor. That is the difference. So we can connect 34 keys. So what happens? The scan lines will be produced by your microprocessor. So it will try to activate each row and try to read the corresponding column bits. If a valid key press is there, then the corresponding return lines will have a different value. So thereby it can identify a key press. So first let us assume that the CPU generates the scan lines like this. For example, if it gives 1110, row 0 will be selected. So 1110 SL0 line will be activated. If it is 1101, then SL1 will be activated. Then 1011 SL2 will be activated. 0111 row 3 will be activated. So this scan lines, this combination will be given by your CPU. And after giving a particular combination, either selecting row 0, row 1, row 2, row 3, it will try to read the return lines RL0 to RL7. So let us see this with an example. So let us consider that currently the CPU is scanning row 3. So row 3 means SL3 row by sending 0111. And the received information in the RL0 to RL7 is 10111111. So which means it indicates the key or the switch or the sensor at 6th position, right? So this is the 6th position, it got pressed or it got activated. So that can be easily identified by visualizing the RL6 line going to 0. So when the RL6 line goes to 0, it means the 3rd row, 6th bit position switch or matrix sensor got activated. And how this data will be saved in your FIFO RAM? FIFO RAM is a 8 byte data can be saved. So 8 key presses can be saved. So in each byte, I have information about a key press. So here you see the MSB part. 7th bit and 6th bit represents the status of your control and shift key. Whether control key is pressed or shift key is pressed, that is indicated by the 7th bit and 6th bit. In order to indicate the row, so row, here I have the third row. Okay, I have only 4 rows, 0, 1, 2 and 3. So since the scanning is done on third row, so it is 0, 1, 1. And which bit in your return is activated? 6th bit. So which means it is given by 1, 1, 0. So thereby this content will be available in your FIFO RAM. If I have another key press, depending upon that I have a row value and the column value will be indicated. Next mode is your encoded mode. Again, this mode is also applicable for your keyboard mode as well as the sensor matrix mode. The only difference is the switch will be replaced by a sensor, digital sensor. So here in encoded mode, we can interface more number of switches. How it is possible in the sense, we make use of a decoder IC. So I can use a 3:8 decoder. In that case, I take 3 lines, 3 scan lines, and 8 outputs will be generated by the decoder. From 3 scan lines, 8 outputs will be generated. So 8 outputs in the sense, I have 8 rows and 8 columns, which means 64 keys are interfaced. In addition to the 64 keys, I also have special key, shift and control key. So altogether 66 keys can be interfaced in your encoded mode. Right? So we make use of a decoder to convert your scan lines into corresponding rows. So for example, if my scan line is 0, 0, 0, then row 0 will be selected. 0, 0, 1, row 1 will be selected. 1, 1, 1, row 7 will be selected. So depending upon my scan line, the corresponding rows will be activated. Once the row is activated, then the CPU will try to read the column value RL0 to RL7. Then that value will be loaded into the FIFO RAM. So now in encoded mode, let us see how it is being loaded. So again, let us consider that currently the CPU is scanning row 5. So row 5 it is going to scan, which means what should be the value of SL0 to SL2? For row 5 it is 101. Right? For row 5 it will be 101 in SL0 to SL2. So 101 indicates a row. So here it is shown in the FIFO RAM 101. And the corresponding received information is 10111111. In that case, again 6th bit is activated. So since the switch or sensor is activated, that is indicated by this 6 value. 110 is nothing but 6. Then the MSB part, control and shift, indicates the status of your shift and control keys. So this data will be loaded in your FIFO RAM for a valid key press in encoded mode. So now let us interface this keyboard with a 8085 microprocessor in IO mapped IO mode. So IO mapped IO in the sense, the IO addresses will be indicated by a 8-bit value. IO addresses will be indicated by a 8-bit value. Whereas in a memory mapped IO, 16-bit address will be used to identify a IO devices. So here we connect D0 to D7 of your 8085 microprocessor to D0 to D7 of your 8279 IC. Then A0 will be given by your CPU. So if A0 is 0, data register will be selected. If A0 is 1, control register will be selected. So other lines in IO mapped IO, A1 to A7 represents the chip select lines. So this is used for chip selecting the IC. Then I have IO read, IO write connected to RD bar and WR bar, and the reset out of your microprocessor gets connected to reset, and clock out of your microprocessor gets connected to clock. So once a valid key press is there, once a valid data is available in the FIFO RAM, that information can be passed on to the CPU through an interrupt signal. So an interrupt can be generated and it can be connected to an interrupt line of your 8085 microprocessor. So 8085 supports 5 interrupts: trap, RST 7.5, 6.5, 5.5 and INTR. So you can connect this interrupt line to any of this interrupt lines of your 8085. So here you see we used 3 scan lines connected to a 3:8 decoder, thereby 8 rows are generated, and there are return lines RL0 to RL7, each connected with a switch. So each interfacing of a row with a column is connected with a switch in a keyboard mode. In a sensor mode, each switch is replaced by a sensor, which is a digital sensor. In a memory mapped I/O mode, the main difference is 16-bit address lines will be used for identifying the I/O device. So again, A0 represents data register, A0 equal to 0 means data register, A0 equal to 1 means it is control or command register. So we use other lines A1 to A15 for chip selection. Then MEMR is connected to read signal, MEMW, memory write, is connected to WR bar. Same way reset out, clock out, and once the interrupt is generated, it can be connected to interrupt pin of your 8085. There are return lines, shift and control lines, then scan lines. So this is how we can interface your 8279 IC in a keyboard mode with your 8085 microprocessor. Next, let us discuss the second part. So how to use this 8279 for interfacing a 7-segment display. So 7-segment display, here I have shown a 7-segment display. It consists of 8 segments. So 7 segments are A, B, C, D, E, F, G, and there is also a DP, data point, is available. So this 7-segment display can be activated by the 8279 IC. So to display a character into 7-segment display, we have to store 7-segment code in the display RAM location. So we can store up to 16 bytes of data. So 16 characters can be displayed one by one on a 7-segment display. To write data into the display RAM, so CPU needs to write the data onto the display RAM. So one special command is applied. So what is that special command? So it's a 8-bit value. So here you can see 100 will be used for identifying it as write to display RAM. Okay, so this indicates if I put 100 in the MSB part, then it means the CPU is going to write the data onto your RAM. Then the last 4 bits indicates the location of your RAM, which character will be sent. So 16 characters can be stored in the display RAM. Out of the 16 characters, which character will be sent out? So that RAM location is given by this 4 bits. AA. And this center bit is used for indicating it whether it is in auto increment mode or auto normal mode. So auto increment mode in the sense, once a particular data is sent out, then automatically the address will get incremented. It points to the next address location. So that is called as an auto increment mode. So this command gives an indication that the CPU is going to write the data onto the display RAM. In the display RAM, in which position it is going to write the data, and after writing the data, whether it is in an auto increment mode or not, so that the subsequent data can come to the incremented address. Same way, the CPU can also read from any RAM location. It can read from any RAM location. That is identified by again 011. So 011 pattern indicates read from a display RAM. From which location is given by AA. So after reading a data, the address can be incremented to the subsequent location. Thereby, the next read operation can be taken care of. So that is using auto increment. So 100 represents the CPU is going to write a data onto the display RAM. 011 represents the CPU is going to read a data from the display RAM. So let us take a simple example. CPU needs to write at RAM location 4 in auto increment mode. So the RAM pointer is loaded with address 4. So first it is going to write a data onto address 4, then it will get automatically updated. The address will get incremented to 5, then it can put the next data. So in order to do that, we will see how to write a programming for displaying ABCD in the 7 segment display. So first we take this 8 bits 100 represents 100 represents it's a write to display RAM. Then next one indicates it's a auto increment mode. Then 0100 represents address location 4. So the CPU is going to write a data onto address 4. After writing it, it will go to automatically incremented to 5. So we move this data to accumulator. From accumulator, we send it to D1. So where this 1 represents, it is a command register. Other bits. Okay, D1 is a IO address, IO mapped IO address. It's a 8-bit address. So the A0 is 1, which means write the data into command register. Other bits A1 to A7 will be used for chip select lines. Then next data is A1. So A1 is nothing but 10100001. So here you see when I put this value onto the 7 segment displays. So this LSB is your A, B, C, D, E, F, G and D. So which means we are activating B. So 0 will activate the corresponding segment. So B, C, D, E, G are activated, which means it is going to display a character D on the display. So A1 is sent to A and this A is sent to D0, where 0 represents it's a data register. Next, similarly C6 will be sent. So C6 will be sent to D0, which means the character C will be displayed. Next, A3 will be sent to accumulator. From accumulator it goes to D0, which means character B will be displayed. Same way 88 is sent to accumulator. From accumulator it goes to D0, which means character A will be displayed. So in RAM location 4 we have character D, RAM location 5 we have character C, RAM location 6 we have character B, and RAM location 7 we have character A. So that is how the data is written onto the display RAM. Now let us see a program to read a data from a display RAM. So to read a data, the first 3 bits should be 011. To read a data from a display RAM, it is 011, then it is an auto increment mode. Then we are going to read from location 0110, so 4th location. So move this data to accumulator. From accumulator it goes into the command register. Then we use a in command in instruction to read the data from a data register. So thereby in RAM location 4 we have A1, so which we have already stored here. You can see in 4 we have A1. So this A1 will be read. So after that the address location automatically gets incremented to location 5. So thereby C6 will be read. So the first in instruction will read A1, second in instruction will read C6 by the CPU. So this is how we read from a RAM location. Next one is again the 7 segment display can be in 2 modes, encoded mode or in a decoded mode. So in encoded mode we can interface multiple 7 segment displays, whereas in decoded mode we can interface less number of displays. So for example in a encoded mode we use a again decoder. We can use 4:16 decoder. I can give the 4 lines SL0 to 3 and each output from the decoder can be used for selecting a particular display. So I can connect 16 displays. 16 7 segment displays can be connected and each 7 segment display can be selected by using one of the output from your decoder. And the character to be displayed will be sent through A0 to A3 and B0 to B3. So 8-bit data will be sent here. So first we select a particular display and put the corresponding character to be displayed onto that 7 segment display. So here in encoded mode 16 up to 16 7 segment displays can be connected. In case of a decoded mode only 4 7 segment displays can be connected. So here we use individual select lines or scan lines SL0 to SL3 for selecting the individual 7 segment displays, and the corresponding character to be displayed, the binary bit pattern will be given by A0 to A3 and B0 to B3. So this is your decoded mode. So now let us see how to change the modes between keyboard mode and a display mode. So display controller mode settings. So command 000, first 3 bits, if it is 000, it means we are programming the operating modes of keyboard and display. So operating modes of keyboard and display are being programmed. So the 3 least significant bit decide the keyboard mode, then the B3 and B2 represent the display mode. So first let us see the keyboard mode. So 3 bit we have 8 combinations. So 000 means it's a encoded scan keyboard mode 2 key lockout. So 2 key lockout in the sense when 2 key is pressed simultaneously, whenever there is a 2 key has been pressed simultaneously, only the first key which is pressed will be identified. The second key will be rejected. So that is 2 key lockout. So this is in a encoded mode, encoded scan keyboard mode, 2 key lockout. 001 means it's a decoded scanned keyboard again in 2 key lockout. So if 2 keys pressed simultaneously, only the first key will be recognized and the second key will be ignored. Next one is 010. So 010 represents again encoded scanned keyboard mode, but in N key rollover. N key rollover in the sense, if I have multiple keys pressed simultaneously, all the valid key presses will be saved in the FIFO RAM. So all the key presses. So in the first case, only the first key will be identified. Subsequent key press will not be identified. Whereas in N key rollover, if I press 4 keys simultaneously, all the 4 keys will be recognized and it will be saved in the FIFO RAM. Same way we have a decoded scan keyboard in N key rollover. Then 100 is for encoded scan sensor matrix. 101 is for decoded scan sensor matrix, and 110 and 110 is for strobed input mode in encoded and decoded mode. So for display, B3 and B4, 2 bits are there, so I have 4 combination. So here 00 means 8-bit character displays, left entry mode. So the characters will be entered from left to right. Whereas in a 10 and 11, the characters will be entered from right. So it will go from right to left. So here 0001 represents left entry. 8 displays can be interfaced or 16 displays can be interfaced. In case of 10 and 11, right entry, 8 displays or 16 displays can be interfaced. So now let us look at a left entry mode. So 16 characters, left entry mode. So 16 displays, let us assume 16 displays are there. So 16 displays, each display is going to get a data from a RAM location. So 16 bytes are there in the RAM location. For example, let us take this is the first display, it will get a data from 0000. Next display will get a data from 0001 location. So like that it goes on. So 1111 RAM location will be given as a data to your 16th display. So now the data comes from left side. So you can see the first data comes into 0000 address location. Second data comes to 0001. Third data comes to 0010, 0011. So like that it goes on. 16th data it comes to 1111. And the 17th data it again comes to your 0000. So like that it goes on. This is a left entry. So the data is entered from left to right when I have a display interfaced like this. Let us see a right entry. So right entry is again I have segments connected here. So first segment, second segment, third segment. So like that goes on till 16th segment, and each segment is going to have an address location. So here you see the each segment as a fixed address. In the left entry mode, you can see, for example, the first segment will get always the data from 0000. Second segment will always get the data from 0001. Whereas 16th segment will get always the data from 1111. Okay, you can see it from the left entry. Whereas in right entry, it will get changed. For example, the first segment, you see here, let us take this side. Okay, so for better understanding, let us take this side, right? So the 16th segment, it gets a data from 0000. When the second data is entered, now the 16th segment will get the data from 0001. It will not get the data from 0000. It will get the data from 0001. From the third entry is there, the last segment, 16th segment, will get the data from 0010. Which means here the address changes for each segment when we update the data into the display. So that is how you can see the characters are being moved in a fashion from right to left. So in left entry mode, each segment is something assigned with the address from a display RAM. So it will get the data from the display RAM address. Whereas in right entry, the segment is not going to get the data from the same location, it will get the data from different locations. This is your right entry. So in this tutorial, we have discussed about on how to interface an 8279 IC with 8085 microprocessor in both keyboard mode as well as in a display mode, and how to configure it in a keyboard mode and in a display mode we have discussed with 8085 microprocessor. Thanks for watching. Please subscribe for more technical learning. Thank you.